In this video, we are going to focus on the first type of the improper integrals, where this is the one or both intervals are infinite. For the first cases, I try to draw a graph that will make you understand more how to differentiate or make you understand more about how the intervals meet. Okay, so for the first case where the limit is from a finite number of a up to infinity of fx dx. So the graph should be something like this. Okay, let's say the function is something like this. Okay, so the interval start from a, so here is a, and it ends to infinite number. So this whole area, infinite number is something, a very big number. Okay, so this will be something like this. Okay, the second one is from negative infinity to b. So the graph should be something like this, from negative infinity, from a very big number that is negative to so this is somewhere b, and this is from negative infinity, so the interval is from negative infinity up until b. And the last one is the interval from negative infinity to infinity of fx dx. So the intervals will be something from a very big number, a negative number, to a very large number. So this will be the meaning of from negative infinity to infinity of fx dx. To understand how to evaluate the improper integrals, let's say we have a function of y equals to 1 over x squared. So here we try to draw a graph of y equals to 1 over x squared. So here is y-axis and here is x-axis. Okay, let's say we want to find the area under the curve start from the lower limit is from 1. Okay, and then let's say we want to find up until the interval of 2. So we can find the area under the curve of this function, where we start from 1 to 2 of 1 over x squared dx. So we can solve this, where we get negative 1 over x, where the limit is from 1 to 2. So we have negative 1 over 2 minus negative 1, or we can write it as negative 1 minus 1 over 2. So the area under the curve of y equals to 1 over x squared from 1 to 2 is equals to 1 over 2. Okay, now we extend our limit from 1 to 2 to from 1 to a number of t. So we want to find the area under the curve of 1 up to t. We want to find the area of t here. So we know that we just change the limit from 1 up to t of the function of 1 over x squared dx. So using the same method, so we finally get the answer which is 1 over x from t to 1, and then substituting this we get negative 1 minus 1 over t. So the area of of this, the area under the curve of 1 over x squared from 1 to t is given 1 minus 1 over t. Right now, we extend our t. If we take t approaching to infinity, so the area of shaded region of AT here is AT. Will also approach to limit of AT will approach to t approaching infinity, where this will be equals to limit of 1 minus 1 over t as t approaching infinity. So now we can just substitute our t which is approaching infinity, where we have 1 over 1 of infinity. So 1 over a very large number, you will get it will be approaching to 0. So 1 minus 0 is equals to 1. So we can rewrite this integration of the 1 over x squared from 1 to infinity. Okay, let's say we want to 1 over infinity of 1 over x squared dx. We can write it as a limit of 1 up to t, where t is approaching infinity. So the function is 1 over x squared dx is equals to the limit of, so we solve the integration of 1 over x squared. We have negative 1 over x, where t is approaching infinity. And the limit is from 1 to t. Then we just substitute the limit, which will be 1 over 1 minus 1 over t as t approaching infinity. So we have 1 minus 1 over infinity, or the final answer will be equals to 1. So even though the limit is from 1 to infinite, it is supposed to be an infinite curve. But for this case of 1 over x squared, you can see that the area under the curve from 1 to infinity is equals to 1. So it is a finite number, so it means that this limit is converged. In this example, we can define the integral of a function over an infinite interval in this following way. So the first one, if fx is continuous in the interval from a to infinity, then the integral of fx dx from a up to infinity will be equals to the limit of a to t, where t is approaching infinity of fx dx. And the second one is if fx is continuous in the interval of negative infinity to b, then we can write the integration will be from limit of t to b, where t is approaching negative infinity of fx dx. For these two cases, the improper integral is called as convergent if the limit exists, meaning that it has a finite number. Okay, given that from the previous example, where the integration of 1 over x squared, 1 over infinity here, results into equals to 1. So meaning that this is a finite number. So it means that the limit exists. We can say that the improper integral 1 over x squared is converged to the value of 1. But if the limit is not exist, it means that the integral is diverged. So if the final answer of your function is equals to infinity of negative infinity, this means that the integral is divergent. Now we go to the third definition. So if fx, our function of fx, is continuous in the interval from negative infinity to infinity, then we can write this as equals to negative infinity up to a of fx dx plus the integration of fx dx from a to infinity, where we can write any real number a can be used. For this third case, this integral on the left hand side is said to be converged if both improper integrals on the right hand side is converged. But the left hand side will be diverged if either one or both of the improper integrals on the right hand side is diverged. So it can be diverged if one of the integrals are diverged. Can be converged plus diverged, or diverged plus converged, or both are diverged.